This video is about designing with thermistors. It corresponds to the second part of section 5.2 of Applied Analog Electronics. Now, the point of a thermistor is to measure temperature, and what the thermistor does is it turns the temperature into a resistance. And that resistance was very nonlinear. It went down as the temperature went up, and the curve is kind of messy. Also, resistance is not something we can directly amplify with an amplifier. It's not something we can directly measure with our microcontroller board. Our microcontroller board measures only one thing, and that's voltage. So, how do we convert a resistance that's variable into a voltage? And the simplest way to do that is to use the only circuit that we know, voltage divider. And so we can take a voltage divider, put the power supply voltage from the microcontroller on one end, ground on the other, and take out voltage in between. And the voltage in between here, we already know from the voltage divider equation, is going to be 3.3 volts times, let's call this one RU and this one RD, RD over RD plus RU. So if one of these two varies, then the voltage will vary. And so what we can do is we can replace one of these fixed resistors with a thermistor. The symbol for a thermistor is to have a resistor symbol, put a T next to it to indicate that it's thermal, and then put a circle around the whole thing so you don't lose the T. So that's the symbol for a thermistor. Now you have two choices of this. You can replace RU with a thermistor, or you can replace RD with a thermistor. And the formula that you'll get here will change. In one case, you would have RD equals the R infinity e to the b over t. In the other case, we'd have RU equals R infinity e to the b over t. And which one of these you choose will determine whether the voltage goes up or down as the temperature changes, as the temperature rises. So if you want something where the voltage rises as the temperature rises, you have to pick the right one of these two to replace with a thermistor. I'm not going to do that for you. The other choice you have to make is, well, this thermistor, the one we're using, has got 10 kiloohms at R25 at 25 degrees Celsius. And so we're kind of stuck with, we've got a particular thermistor we're using. We can't change that easily. But we can change the fixed resistor that's the other one of the two, whichever one is not the thermistor. We can change that because we have a lot of different resistors available. And so that's the other part of your design. The first thing is which one's the thermistor, which one's the fixed resistor, and then how big is the fixed resistor? And what changes? Well, I've plotted here a curve for the thermistor being whichever one it is that makes it get bigger, and picked various different fixed resistors, which I have deliberately not labeled here because I'm not trying to give you the answer. I'm trying to show you how to go about getting the answer. So these are plotted all with GNU plot with a 3.3 volt power supply and different fixed resistors. And I believe this was in fact using the parameters for the thermistor that we have. And you notice that as you change the fixed resistor, what changes is two things. One is, where is this curve the steepest? At what temperature do we get a very steep curve? And how steep is it? So as we change the resistor, we can get both the maximum sensitivity place. Sensitivity, notice, is the derivative of voltage with respect to temperature. The derivative of the output with respect to the input is always our definition of sensitivity. So it's the slope of this curve here. And we have a very high slope at low temperatures. If we pick resistor for optimizing for that low temperature. If we pick a resistor that optimizes for sensitivity at high temperature, then we'll get gentler slope but a wider range. And incidentally, the range that I have on this plot is not really appropriate for the thermistor we've got. Because the thermistor we have had specified on the datasheet that it goes from minus 40 to plus 105 degrees Celsius. I've made my range much bigger than that. Why? Mainly so that I could show you the sort of sigmoidal nature of these curves. So you can see that it's flat as you go to lower temperatures, flat as you go to higher temperatures. So when you're outside the operating range for your circuit, you're not going to get much sensitivity. The voltage is going to change very little when you're at way too high a temperature or way too low a temperature. And so picking the right resistor here is a matter of saying, well, how do I get the maximum slope at a particular temperature? That would be maximizing the sensitivity at that temperature. Or another possible thing you could do is say, I want the voltage to be as linear a function of temperature as I can get, so that the curve is as straight as possible there and not bending. So you can go for maximizing sensitivity or maximizing linearity. And these give you slightly different optimizations to do. Maximizing sensitivity is, well, let's go and look at that in writing. Sensitivity is the derivative of voltage with respect to temperature. Okay, that's sensitivity. If we want to maximize sensitivity, then what we have to do is take the derivative of this with respect to the resistance value. So we say, for what resistance value do we get the maximum sensitivity? So we need to take the derivative of that with respect to whatever our fixed resistor is, and set that equal to 0. And that would maximize the sensitivity. If we want to maximize the linearity, then what we say is, well, we want this thing to be a straight line with respect to temperature. So we take the derivative with respect to temperature, and take the derivative with respect to temperature again, and set that equal to 0. And that would be the point, again, solving this thing for R, and that would be the point at which we have maximum linearity. So there's two different optimizations we could do. They're going to give you slightly different results. And so you have to decide, what are you really trying to optimize? Are you trying to make the voltage versus temperature as straight a line as possible near the operating point? Or are we trying to make it as sensitive as possible at the operating point? And these result in different solutions for what is R. And notice that R there is whatever our fixed resistor is, because all the parameters here for the thermistor are determined by our choice of thermistor. And so the only free variable in the formula here for what's the voltage as a function of temperature, the only free variables are the temperature and the fixed resistor that we're trying to optimize for. And I'm not going to do this calculus for you. This is part of the exercises for this lab. The design work for this lab is to try to pick which of these resistors is going to be the thermistor, and for that choice, get the formula for what is the voltage as a function of temperature, and then optimize by taking derivatives to get what is the value of the resistor which optimizes either the sensitivity or the linearity at a particular operating temperature. Depending what operating temperature you get given, you will get different resistor values. And the way I have done this in the past is that students have done the derivations here, part of the pre-lab, have come up with a formula that says, okay, the optimal resistor value for optimizing for sensitivity or optimizing for linearity is this function of TOP. Then in the lab itself, I have given them, okay, TOP is, and then I give them a value somewhere in the temperature range that's reasonable for the thermistor we're using, and they figure out what resistor they have that's going to come closest to optimizing the sensitivity or the linearity given that operating temperature. And so the design work is to design for a particular thermistor all the different possible values of resistors that might be needed for maximum sensitivity at different operating points, and then plugging in the operating temperature that you're actually going to be given to determine the resistor you'll actually build your device with. So this is the second half of the thermistor lab. The first half of the thermistor lab is characterizing your thermistor to get the parameters for the thermistor, and the second half of the lab is to build the voltage divider, to design and build the voltage divider to get voltage as a function of temperature.